Hello,
Hello.
I'm Wilson.
And I'm Hongzi.
So today we're doing Physics 2 project and our title is...
It's homopolar motor.
So what is a homopolar motor? This is a homopolar motor.
It looks very simple, right? So a homopolar motor is a very simple electrical motor which just requires a battery, a magnet and some copper wire. When we connect the copper wires, the current flows. And what happens when the current flows? It does produce a force that moves in a certain direction.
So some of the theories applied are the Fleming's left-hand grip rule. So what's the Fleming left-hand grip rule? It's actually like this, which have this finger pointing for the magnetic field, this one for the force, the direction of force, and this one pointing for the direction of the current. And we're gonna use this later to determine the direction of the force, of the movement of the force that's moving in a certain direction later.
And the other law that we'll be using is Lorentz law. So basically what is Lorentz law is F, the formula will be applied is F equal to BIL, and F equal to force, B equal to magnetic field force, and I is equal to current, length is equal to the length of the wire. And how about sin theta? Sin theta is the angle between the magnetic force and the current. So in this experiment, because of the magnetic field and the current is perpendicular, so the degree between of them is 90 degrees. So sin theta we will put as sin 90 degree, and which is equal to 1. So in this experiment, we are just using the formula F equal to BIL.
And cancel the 1, because we're taking it as only 1. So some of the stuff you need to prepare for this homopolar motor is a magnet. In this case, we use this disc-shaped super strong mini magnet, AA 1.5 volt battery, or any volt, it's okay, and also the copper wire. So the copper wire, you can always get it everywhere in any store. We tried out with a few designs which actually failed sometimes, and the heart shapes, they all failed, and eventually you just have to try it out, and eventually you will get a final great balanced design like this. So precautions are also taken to use the proper magnet, because like in our first attempt, we actually used this fridge magnet where you can get it anywhere. We tried it throughout the whole day, tried, it keeps on failing, and we got us so fed up until we went back and finally checked with this electric light bulbs, and we check like this, and only then we noticed that it doesn't light up, so it does not conduct electricity. Only then we realized that it's not. But if you see in the case of this shape magnet that you can't really find anywhere, when you connect it, the light bulbs and the battery, as you can see, the light bulb lights up and it does conduct electricity. And so now the setups.
So the setup is very simple. It's first you connect the battery and the magnet. You put the magnet below the battery, but in this case the surface area of the magnet is too small and the battery cannot balance, so we put it on the other magnet so it does balance. So just like this. After that, we put the copper wire over it like this, and it might spin, but the bottom you must contact with the magnet so the current flow. In this case, the copper wire doesn't connect, so we do it and do it some adjust and until it touch it and it maybe can spin. As you can see, it's quite hard to make it balance, but when it balance, it spin like this. So it spin anti-clockwise now. So according to the Fleming left-hand rule. When we change the magnetic pole to like opposite the just now that one, it might show up clockwise spin. Yeah, you can see it's clockwise. See, it's hard to balance. Make it balance again. So after reverse the magnet, and you can see it spin clockwise, and after balancing some, it becomes very smooth and it spins faster. So now
This relates to the Fleming's left-hand rule.
yeah, so Fleming left-hand rule. So the current is this finger. It flows through from right to left, and so you can see the magnetic field is facing downward, and the force is pushing to me. And inversely, when just now the magnetic field are pointing upward, and the current still is from right to left, and it spin, the force pushing towards, and it spin clockwise. Okay, and if you are not clear, I will repeat the Fleming left-hand rule again. So basically, this is the magnet, and we assume that if north pole facing upward and south pole facing downward, so we put our finger, the second finger pointing upward, and the middle finger represent the current is flow from right to left, and as you can see, the force is pointing towards. So the magnet is here, so it pushed the copper wire anti-clockwise. So, and when you reverse the magnetic pole, it becomes like this. So the force pushing toward this direction, and it's totally opposite to just now. So it turned clockwise.
Well, the sad thing of this experiment is homopolar motor actually hasn't found its way to function or contribute in our normal daily lives. But I do believe in the future, where our technology is greater, we could actually apply homopolar motor in automotive, in cars, because as you can see here in Lorentz law, the force or the speed of the spinning is actually directly proportional to the magnetic force and current and the length. So if we somehow could find a way to produce an engine that could actually produce a way that can actually increase the current or magnetic force simultaneously, we could actually apply this and take this homopolar engine, and we can apply it and install it into cars. And other than that, we can also use it as decorations. I mean, who doesn't want a cool little thing like this in your office? It'll look damn cool. It'll make you look smarter.
Oh yeah.
And that's it for our project. Thank you very much for watching. Thank you, Mr.
Thank
Uva,
you.
for all your help. And we're gonna end it here. Thank you very much. Thank you. Ciao.